get ready for an incredible event. Neil deGrasse Tyson just announced that the Sun has unleashed one of the largest explosions ever recorded, an X-2.8 class solar flare, the most intense in 17 years, marking a moment of awe and concern. But what does this mean for us on Earth? How does a burst of solar energy, thousands of times more powerful than usual, affect our planet and daily lives? Join us as we explore this solar spectacle, unraveling the mysteries of this shocking event and its implications for our technologically driven world. Solar flares, the Sun's dramatic displays of energy, are a natural phenomenon. Originating from the Sun's corona, the outermost layer, these flares are a byproduct of the Sun's complex magnetic field. The magnetic field lines can twist and snap, releasing an immense amount of energy that heats the solar atmosphere to millions of degrees. This process accelerates charged particles, primarily electrons and protons, through magnetic reconnection, transforming magnetic energy into kinetic and thermal energy. The result is an intense burst of X-rays and plasma, creating solar flares. But what happens when one of these immense solar flares, like the X-2.8 class, directly targets Earth? The classification of solar flares is based on their brightness in the X-ray wavelengths. There are two main classes, M-class and X-class flares. M-class flares are medium-sized events that can cause brief radio blackouts at the poles and minor radiation storms. However, the more formidable X-class flares are the largest explosions in the solar system, capable of creating planet-wide radio blackouts and long-lasting radiation storms. The energy released in these flares is staggering. The occurrence of solar flares is closely tied to the solar cycle, an approximately 11-year cycle where the Sun transitions from a solar minimum, characterized by few sunspots, to a solar maximum, marked by an abundance of sunspots and heightened solar activity. This cycle plays a crucial role in predicting solar flares and understanding their potential effects on Earth. Agencies like NASA and NOAA are at the forefront of monitoring solar activity and predicting solar flares. Satellites like the Solar Dynamics Observatory allow for the constant monitoring of solar activity, enabling real-time detection of flare occurrences. NOAA's Space Weather Prediction Center provides forecasts and alerts using a network of ground and space-based sensors to gather data on solar events. Protecting satellites involves using hardened electronics, redundant systems, and predictive models. On December 14, 2023, the Sun experienced a significant solar event, emitting an X-2.8 class solar flare, one of the most intense categories of solar flares. This event marked a pivotal moment in solar observation, as it was the biggest flare in the last 17 years. The classification of X-2.8 places this solar flare among the most powerful and energetic types. To put this into perspective, X-class flares are the largest explosions in the solar system, and their intensity is scaled numerically. An X-2.8 flare indicates a flare that is almost 3 times more intense than the baseline X-1 flare. The energy released in this kind of event is immense, capable of producing as much energy as a billion hydrogen bombs. This flare's intensity is significant in its potential effects on Earth. Solar flares of this magnitude can have far-reaching consequences. The radiation from such a flare can interfere with the functionality of satellites in orbit, impact radio communications, and even cause changes in the Earth's ionosphere, affecting GPS and other navigation systems. The event of December 14 was captured and monitored by various space agencies and observatories, including NASA's Solar Dynamics Observatory. This observatory plays a crucial role in continuously monitoring the Sun, providing valuable data that helps in predicting and understanding solar activities. The detailed images and data captured by these observatories offer insights into the complex processes occurring on the Sun's surface and in its atmosphere. The occurrence of such a powerful solar flare during the current solar cycle, which began in 2019, was unexpected. Typically, the solar cycle, lasting about 11 years, alternates between periods of high and low solar activity, known as solar maximum and solar minimum, respectively. The current cycle had been relatively quiet with fewer sunspots and lower solar activity, making the December 14 flare a surprising and noteworthy event. The December 14th solar flare serves as a reminder of the dynamic and unpredictable nature of our sun. It highlights the importance of continuous monitoring and study of solar activity. The data and insights gained from this flare will contribute significantly to our understanding of solar activities and their effects on Earth, aiding in the development of more effective prediction and mitigation strategies for future solar events. The solar flare that erupted on December 14, 2023, was also a disruptor of human-made systems. This X2.8 class flare, as classified by experts, triggered immediate and noticeable effects on radio communications, power grids, and satellites, underlining our vulnerability to solar activities. The solar flare thus points towards profound implications of such solar events on our increasingly technology-dependent world. One of the most immediate impacts of the flare was on radio communications. Solar flares are known to emit intense bursts of electromagnetic radiation, which can ionize the Earth's upper atmosphere, particularly the ionosphere. This ionization disrupts the radio signals traveling through this layer, leading to interruptions in high-frequency radio communications. For instance, aviation, maritime, and ham radio communications, which rely heavily on high-frequency bands, likely experienced significant disruptions during and after the flare. These disruptions can last from minutes to hours, depending on the intensity of the flare and its interaction with the Earth's atmosphere. The flare also posed a threat to satellite operations. The intense radiation and energetic particles released during such an event can damage the sensitive electronic components of satellites. This damage can range from temporary malfunctions to permanent failures, depending on the satellite's exposure to the flare and its protective measures. Satellites in geostationary and polar orbits are particularly vulnerable due to their exposure to the Earth's outer magnetic field, where charged particles from solar flares are more likely to penetrate. Moreover, the flare's potential impact on power grids is a concern. Geomagnetic storms induced by solar flares can create electrical currents in the Earth's magnetosphere and ionosphere. These currents can find their way into power lines, potentially overloading transformers and other components of the electrical grid. While modern power grids are designed with protective measures against such events, the intensity of an X2.8 class flare presents a considerable challenge, raising the possibility of power outages and disruptions in power supply. Apart from these disruptions, the solar flare created a mesmerizing display of auroras, more commonly known as the northern and southern lights. The interaction of the energetic particles from the flare with the Earth's magnetic field and atmosphere resulted in spectacular light shows, visible much farther from the poles than usual. These auroras were also visible in lower latitudes, offering a rare and stunning visual treat. Social media platforms were abuzz with user-generated content capturing these auroras, showcasing their widespread visibility and the public's fascination with this natural phenomenon. NASA's Solar Dynamics Observatory is a cornerstone of our scientific efforts to understand and predict solar activities. Launched in 2010, the Solar Dynamics Observatory's mission is to provide a deeper understanding of the Sun's influence on Earth and near-Earth space by observing solar activities in unprecedented detail. The Solar Dynamics Observatory is equipped with sophisticated instruments that make it possible to capture high-resolution images of the Sun in various wavelengths.